So just again a reminder, so today, this afternoon, Zvi's colloquium will start at 2:20 at the department. So we'll have Zohar to give us the second part of this lecture.
Okay. Introduction to the subject of quantum field theories with the random coupling constants. So I'll start by maybe a very short introduction. I'll start with some motivation for why this problem is interesting physically. So as you all know, quantum field theory in its present form, meaning that we understand that there are conformal field theories, and they can be deformed, and they can flow to new conformal field theories. This whole structure originated from statistical mechanics. So the prototypical problem that people have considered is the Ising model. So you have some d-dimensional block of spins.
Zohar?
Yes.
I think your tag is hitting the microphone.
So there is some block of spins. And for simplicity, let's assume that the sites are labeled by I. So I some vector in d-dimensional space. Okay, and at each I we have a spin. So Si, which is either 0. Okay, either let's say 0 or 1. Or let's say -1 and 1. So either -1 and 1. So either it points downwards or it points upwards. And the Ising model says that the energy of this spin configuration, so given the spin configuration, the energy is minus J, and then you sum over all the neighboring points. So this notation means that we sum only over I and J, which are neighboring points. So it's the sum over neighbors. And then we write something like Si, Sj, and then there may or may not be a magnetic field, an external magnetic field H, to which the system responds according to the total magnetization in the sample. Okay. So this is the Ising model in 2 dimensions. Yes?
It is ferromagnetic rather than antiferro.
Yes, so I will consider for simplicity the case of J bigger than 0. In this case, spins would like to be in the same direction. Nearby spins want to align in the same direction. Okay. The other case has some other issues. So this model. So now we consider the partition function, which is e to the minus h over t, where t is the temperature. And we, of course, sum over all the spin configurations. So over all the possible spin configurations. And that provides us with the partition function of the theory, from which all the thermodynamic quantities can be derived, as you all very well know. Okay. Now, how does that connect to quantum field theory? So there is a special temperature, Tc, around which something remarkable happens. So this temperature exists only for the Ising model in dimensions bigger than 1. I'll explain shortly soon why that's the case. But if the number of dimensions is any number bigger than 1, then there is this critical temperature Tc, around which one develops long-range correlations. So are long-range correlations. So spins which are very far apart start killing each other. And thermal fluctuations. So thermal fluctuations become somehow less important. At very high temperatures, of course, the spins don't kill each other because thermal fluctuations are very large. At very small temperatures, so at very high temperatures, spins don't kill each other because thermal fluctuations are large and they wash out any means of the spins to communicate. At very small temperatures, all the spins want to point in the same direction. So the long-range correlations are kind of trivial. And there is a critical temperature where there are power laws. So there are long-range correlations, and there are various power laws. So for example, if you compute the spin at some point I, and then the spin at some other point I prime, and they may be very far apart, you would find some exponents of the sort where r is the distance. So we can write I minus ij, I minus I prime, and you would find something like some 2 minus some exponent, which is usually called eta. And eta could be dependent on the number of dimensions, and we may or may not be able to calculate eta analytically, but there is a power law of this sort, okay, around the critical temperature. And when you get very close to the critical temperature, so it's exact only at the critical temperature, but very close to it, there are still very long-range correlations. They're just damped at the long distances. Okay, so this is a quick review of the phenomenology of this model. Now, in quantum field theory, so near this point, when T goes to Tc, because the correlation length is so large, you don't see the lattice structure anymore. So we don't see the lattice structure. Right? So we don't see the lattice structure because the correlation functions are so long range. If you look from afar, it seems like one continuum. Okay? And this is where quantum field theory arises, because there is a good continuum approximation. So we have a continuum approximation. And this continuum approximation is given by the Landau-Ginzburg model. So we write a quantum field theory, which is ddx. And then we write grad. So the spin becomes some variable in the continuum, which is continuous. So some field phi. And we write this kind of thing. Mine plus lambda phi to the 4 plus, okay, this is usually called u. And then there's r phi squared plus h phi. So this is the kind of field theory that you would write in the continuum to describe the Ising model. So that's the energy density of the Ising model near this, and this is a valid description here near Tc. Now, this parameter here, it's like a master. And if you turn it on, then of course you won't have long-range correlations anymore because the theory becomes massive. And indeed, this parameter is proportional to T minus Tc. So when you're at the critical point, you want to set it to 0, essentially. If you turn on this parameter with a positive sign, there will be one vacuum, which is phi equals 0. And that corresponds to the high temperature vacuum, which is called a disordered phase. If you turn on this parameter with a negative sign, then we have something like the Higgs potential, because it's destabilized near the origin. And these two vacua are the two ordered phases of the Ising model, which are related by a Z2 symmetry. So the spins can either all point up or all point down. These are two low energy configurations. H is an external magnetic field, which breaks the Z2 symmetry. So if you don't turn on H, it would not be generated. It breaks the Z2 symmetry. Okay, so this is the continuum description. So H is the magnetic field, and R is proportional to T minus Tc with this sign. And U flows to some fixed point, okay? So you can put U star. There is a fixed point, and U flows to this fixed point. Now, this model for dimensions bigger or equal to 4, as you know, this model is infrared free. So the exponents, so all the correlation functions, sorry, this coupling becomes infrared free. at 4 dimensions and above. So all the correlation functions are given by those or those of free field theory. So we get free field theory. And this exponent is then easily calculable. It's just a 2-point function in free field theory, which in 4 dimensions is 1 over x squared. So in 4 dimensions, that would be 0. But you can just calculate it using free field theory for any number of dimensions bigger than 4. Now for any number of dimensions smaller than 4, so strictly smaller than 4, but bigger than 1, this is an interacting model, because this is relevant in the free field theory point. So it goes to some strongly coupled fixed point. We can turn off R and H, and just to calculate these critical exponents. And this is the Ising model. The Ising model in this range is a hard problem. In 2 dimensions, it's exactly solvable by the Onsager solution. It's dual to a free fermion, so there is some non-trivial duality. In two dimensions, it's solvable. But between 2 and 4, it's a very hard problem that we can only solve maybe using Monte Carlo simulations or maybe recent bootstrap techniques, which are also numerical by nature. But maybe they're probably more efficient than Monte Carlo if you just want to get the critical exponents. So this is the phenomenology of the model. Are there any questions about it? Now I'll describe what's the next step that I want to discuss. This is classic stuff from the 70s, or maybe even from before. Now, the problem that arises, so suppose you want to experimentally measure these critical exponents. So to measure them experimentally, you need to set h to 0 in the laboratory, okay? Otherwise, the exponents would be shifted, the vacuum would be shifted, and so on. So there will be some mess. So you need to set h to be exactly 0. But in practice, this is very hard. Because, for example, you prepare some sample of spins of some alloy that looks like the Ising model. There will be some disorder, and there will be some maybe perturbations, and the magnetic field could not be really set to strictly 0. It could be very small, but maybe not exactly 0. And the idea is to try to understand what would be the effect on this phase transition if you don't know the magnetic field. So now we take the point of view that instead of saying that we know the magnetic field, this is the classic point of view and it's 0, we can take the point of view that we just don't know the magnetic field. So we would say that the magnetic field is on average 0, let's say, but at some given point x, it would fluctuate like a Gaussian variable, and there will be some variance, which we can call c squared. I usually call it c squared, but in the literature it's usually called delta. Nevertheless, let's keep this notation. So you essentially say, okay, you say that you declare that you are ignorant about the magnetic field. It's a random variable which is on average 0 at every point. But there is some chance that at any given point it would not be 0, and it fluctuates like a Gaussian variable at every given point, independently of neighboring points. So this is the simplest short range. So this is some short range correlation of this random magnetic field. Of course, you can also generalize that, and you can decide that your magnetic field is unknown, but it has long-range correlation. But this is the simplest assumption, that at every given point, the magnetic field just fluctuates regardless of what it does at some other nearby point. Okay, so now the problem is to understand whether under these circumstances there would still be a phase transition. Okay, so this problem, I mean, it's of practical importance because when people make measurements, they want to understand the effects of unknown perturbations. But it's actually interesting just by itself theoretically. People in statistical physics and condensed matter physics study this problem not just because it's interesting practically when you want to make measurements, but it's actually interesting theoretically to understand the consequences of some randomness in the coupling constants on the phase transition. It's actually a very rich theoretical problem that people like to study on its own. Now, the thing is that, let's say that C is very, very small. So suppose C is tiny or infinitesimal. So it's a very, very small parameter compared to the energy exchange between two spins. So you might have thought that because the magnetic field doesn't have any decent chance of becoming large because the variation is so tiny, it won't affect the phase transition very much. And that's actually false. So because there are long-range correlations at the critical point, even a tiny, tiny randomness in this external coupling constant may induce very radical change in the nature of the phase transition, in the critical exponents, and so on.
But only if you go to distances large compared to 1 over C or something.
Yes. So even if C is tiny, it would have far-reaching consequences for the nature of the phase transition for a large enough sample. Yeah. So even if it's tiny, it can have far-reaching consequences. Okay.
Sorry.
Yes.
Just want to clarify. In the original case, when H is a constant, would you call it a long-range correlation?
H is just 0 in the original case, or constant. It's given. It's known.
If it's constant, would you call it long range? Because every point you have the same magnitude.
No, but it's not fluctuating. It's just given. Here, these brackets do not stand for the original correlation functions. This is.
I understand. Yeah.
This is the average. We're averaging over quantum field theories with some property for these external coupling constants. Okay, with some given distribution. So in this case, it's short range. Yes. Okay. So even if C is tiny, it can have very far-reaching consequences for the nature of the phase transition, and there are several options. So let me just list several logical options. 3 logical options. And I'll try to show you examples where all of them are realized. So the first option is that actually this kind of randomness in some cup. So first of all, just one comment before I list these options. Here I've discussed the idea that the magnetic field is random. But it doesn't have to be the magnetic field. It could be the coupling J. It could be any coupling. I mean, realistically, if you think about realizing the item model, any of these couplings in the Hamiltonian, so U, R, H, they could all be random fields. For example, you may not know the binding energy of 2 nearby spins, it may be fluctuating. So any of the couplings could be random. And you have to study separately, case by case, what does it do? Okay. So H is just an example, but you can think about J as having a tiny random component. And so one has to study this case by case. So the 3 options are that such randomness does not change the critical exponents, so it does not change the critical exponents. So this is one option, that it just doesn't change critical exponents. It doesn't change the nature of the ordered phase. It doesn't change the nature of the disordered phase. It doesn't do anything interesting. And in that case, you would just say that this is irrelevant. The second option is that it does not change the nature of the ordered phase very much, but it does change the critical exponent. So does change the critical exponents. Okay, so maybe the ordered phase where all the spins are aligned would look more or less the same, but the critical exponents that describe how the phase transition is achieved would be different, and you would be interested in calculating them or devising some theoretical scheme for how to calculate them. And the final option, which is the most violent, is that actually the phase transition completely disappears. So it's rounded, and there is no more an ordered phase, there is just a disordered phase, and there is no phase transition to an ordered phase. So the phase transition disappears.
So in the case of the short range correlation for H, how is this different from just deforming the action by some local operator, because you can make a Gaussian ensemble for H?
Yes.
To figure it out.
This is a great question. This is one of the main things I want to explain. So what she asked is that what she is asking is that we have this Hamiltonian, which we need to average to calculate the usual thermal correlation functions, right? We average over the spins, and C suggesting to just put an exponent e to the minus h squared, and in that way to achieve, and in that way you can just like reduce it to a known property quantum filter. You just integrate out h and you calculate the flow. So you'll see that it's actually very, very different from that, because averaging the partition function is not a good idea. You need to average the free energy. So what you need to average is the log of the partition function. And it changes the problem completely and very, very dramatically. So I'll explain that point very carefully soon. Okay, so the phase transition disappears. That's the most violent possibility. And that's actually what happens in the Ising model. In this example was H in 2 dimensions. So the phase transition of the Ising model in 2 dimensions, which famously was solved by Onsager, is known to disappear once you allow even a tiny variance in the magnetic field. So this is realized in the Ising model in 2 dimensions. I mean, this is experimental stuff, experimental data. This is realized in the Ising model in 2 dimensions. In 3 dimensions, in the Ising model, the critical exponents are believed to change. Nobody knows how to calculate the new critical exponents. That's what happens. This is if the magnetic field is random. If the binding energy is random, then the critical exponents change, but not by too much, and one can probably calculate it. And this is what happens, for example, if you look at random binding above 4 dimensions. It would not change the critical exponents of the free field theory. So there are various options, and there are many. All of them are realized in various scenarios. So let me give you some qualitative arguments for the effects of a random magnetic field. These are quite old, but I need to review them. They're very beautiful anyway. So I think, yeah, the challenge here is to understand exactly when is this realized, when is this realized, and when is this realized. And these are all open problems. I mean, no, sorry. This can be understood. It can be understood when it does not change the critical exponents. But when it does change the critical exponents, we don't know necessarily how to calculate the new critical exponents. And when the phase transition disappears altogether, it's also not known. So this is the challenge, and I mean, I cannot adequately really address the challenge, but in some examples one can solve the problem and see what happens. Okay, so let me give you some qualitative arguments. So let's consider a sample of spins. And the idea is to have this random magnetic field in mind, even though the other problems are also interesting. So the idea is that we look at some region, sub-region of size L, typical size L, of spins. Okay? And we're looking at very small temperatures. So we're looking at T, much, much smaller than Tc. And by that time, all the spins point in the same direction, either up or down. Usually, that's a good, so usually you would say that there is this region of size L, and suppose all the spins in that region would want to flip sign. How much energy would that cost? That would cost L to the power d minus 1, just because there are nearest neighbor interactions all over the boundary of that region, and flipping all the spins would cost you an energy which is proportional to the area of that region. So this is the energy that would cost you just to flip all the spins, and this is why there is no phase transition in 1 dimension in the usual story of the Ising model, because it just costs a finite amount of energy that doesn't grow with L, and that leads to the washing out of the ordered phase. So there is no ordered phase that equals 1, but above d equals 1, there is an ordered phase because it costs an ever-increasing energy to flip spins in a big part of the sample, in a large part of the sample. So that's the usual term that we get in statistical physics. But now we have this additional component of a random magnetic field. So there is a magnetic field that is random. We don't know what it is. And there is a probability that it's not zero. That the probability is dictated by that. And it's interesting to understand how does that affect the scaling. So how much energy would you gain, possibly, from flipping all the spins in some region. So the idea, let me just write the answer and explain why it's true. So the idea is that once you have a random magnetic field, there is a new term in the energy balance, which is going like d over 2. Where is that coming from? So there is a random magnetic field at every point, and you just sum and now this is a problem of random walk. So there is a random guy sitting at every point, and you need to sum L to the power d random variables. So we have L to the power d random variables because there are L to the power d points. But because they're random, as you know, the variance goes like the square root of that. So this is why there is d over 2. So this is the famous square root of n variance of a Gaussian, of a sum of many random fields. So possibly, flipping all the spins may gain energy that scales like L to the power d over 2 just because they become aligned with a magnetic field, which is random. Okay, so you can possibly gain that much energy by flipping all the spins. Is that clear? It's an important argument from the late 70s by Imbri and Ma that gives some intuition to the problem.
So there will be some regions where you will want it.
Yes.
Some regions where you would.
Yes, there will be some regions where you could gain energy that scales like that by flipping all the spins. Okay, so I assume it's clear? Yes?
How did the length of the zigzag path get turned into length of smooth path in the...
Oh, you mean why is this the smooth region?
No, I mean, if you start with the lattice
Yes.
model, then you would expect, let's say, the first term would be, let's say, in the case of d equals 2, it would be this kind of length of the zigzag path, which isn't quite the same. So it's not exactly proportional to the length of the smooth curve it approximates. But you say that at the end of the day,
Well, near the critical point, you don't see the lattice structure. And the system is divided into regions of spin up and spin down.
I guess that is kind of answer one would expect. We're just not quite seeing how it gets turned into this. Since it's naively you think that. Okay,
I mean, this argument is very beautiful, but it's not quite precise. People worked for at least a decade making this argument that precise. But in the end, it gives the right answer. So you see what happens. You get d bigger or equal to bigger equal to, sorry. So only in this case, now we have a phase transition. Otherwise, the ordered phase just disappears. And that's very dramatic because the usualizing model that we like and love and in 2 dimensions just disappears. There is no more phase transition, but there is a phase transition above 2 dimensions. Now, there is another argument of this sort that is very important, and I'll explain it in more detail. So far I've discussed the Ising model, where the spins could point either up or down. But an interesting variation of that is the continuous spin model, where the spin could point in, so the spin is just a vector in d-dimensional space, okay, which is maybe a more realistic model, you could say. And in that case, so the spin now is an element of Rd itself. It's a vector in two-dimensional space. And in that case, the crucial difference from the Ising model is that in the ordered phase, the spins all align to be in the same direction, but they can be all rotated simultaneously with very little energy because they are continuous and there is a Goldstone mode. Okay, so in that case, the ordered phase has a Goldstone mode. Ordered phase has Goldstone modes. Okay, and it's interesting to repeat this kind of argument in the presence of Goldstone modes to see what comes out of that. So,
Good question.
yes.
You begin with a ferromagnetic spin system, and I suppose spin system is not gapless. Then how can you take the quantum reality?
You mean the ordered phase is not gapless? Yeah, so in this example, the ordered phase is not gapless because there are Goldstone modes, but the continuum limit is just a free filter. I mean, it's a Goldstone filter. There is no problem taking the continuum limit. Okay, so let's